Okay, 10:20. Thanks everyone for being here. My name is Gami Shrestha. I'm one of the co-chairs of this oral session. We also have a poster session and an e-poster session this afternoon, so please join us there. The topic of our session is science-based gigaton-scale carbon dioxide removal, or CDR, strategies for monitoring, measurement, reporting, and verification. So we have an exciting set of talks. Each of them have 10 minutes. So all the speakers will see a yellow warning light here blinking when it's about 8 minutes. So please wrap up your talks. And if you have questions, please hold for the audience, if you have questions, please hold your questions till the end. We'll have 10 minutes at the end of the session for Q&As. So please stay till the very end. I'd like to introduce my co-conveners and co-chairs of the sessions. We have Colin Averill here, Alison Markland, Judy Drexler. Oh, she's with Judy. Hi, Judy. And then Peter Warwick, Christina Bartowicz. Over here, did I miss anyone? We also have Pam Chu. I don't know if she's here, but you'll see us throughout all the sessions. With this, let's move on to the first talk by Jonathan Lambert from Isometric.
Okay, so thanks, Ari. No, thanks to the conveners for having us. I'm super excited to kind of be giving the first talk in this session because I feel like what we're going to talk about in this 10 minutes will set a good stage for kind of some of the deeper dives some of the presenters are giving throughout the talk. So I'm Jonathan Lambert. I'm the program manager on the science team at Isometric. I'll introduce Isometric a bit more later. Like quite a few of us in the room, I think, am a paleoclimatologist and geochemist kind of turned kind of CDR person now. So thanks again for everyone for coming and for the conveners for inviting us. Brief intro, I'll tell you a bit about Isometric. One quick slide, I'll motivate our work and talk about what we're doing in the applied MRV space, spend some time giving the current scope of the CDR landscape and the MMRV landscape, and we'll spend most of the time talking about what we're doing to build consensus and build collaboration in this space, specifically as it relates to protocol development across pathways. And then at the end, we'll talk a bit about the future work we can all do together. And so what Isometric is we're a science platform and registry for durable carbon removal. Durable, by our definition, is greater than 1,000 years. The science platform we have is the part of our website that's completely separate from the registry where CDR companies, our suppliers, as we call them, can list data and talk about their processes completely openly. Anyone can access the science platform. And so this can spark discussion and feedback on processes and data across the CDR landscape. The registry is where you can list credits and track them from removal to retirement. So you can see, ensure no double counting and ensure that you can see kind of every step along the path of ownership of those credits. And so these are our core tenets in all the work we do: rigor, transparency, and collaboration. They'll come up organically throughout the talk, so I'm not going to belabor them here. But so kind of moving into kind of why we think we're needed in this space for a science platform and a registry. So CDR is kind of rapidly growing as a space and expanding, driving more and more suppliers and pathways. And so it's becoming harder and harder to kind of keep up with what's going on. So we're hoping to provide a space where we can critically evaluate everything that's going on. On the registry side, if you've been following the kind of carbon credit space over the past couple of decades, a lot of registries have had some trust and credibility concerns, specifically when it comes to additionality and durability. And so we're hoping to kind of learn from this and build upon it with our registry. And then finally, on the science side, buyers of carbon removal often don't have very large science teams and don't have the capacity to do this quite onerous process of vetting high quality carbon removals. At Isometric, we have 12 scientists whose sole job is to kind of look at these high quality removals. And so this not only benefits buyers by like making sure the purchases are good, but it also leads to ensured climate action, that one credit is actually one kind of ton of carbon dioxide removed from the atmosphere. So making sure the atmosphere actually feels the effects of the carbon dioxide that we're removing. And so we're all here to talk about MMRV today. MMRV and CDR are kind of intrinsically connected. And so with the rapid advancement of CDR and these different pathways, we need a rapid advancement of applied science and efficient collaboration. And so with that, I'll give a brief overview of the MMRV landscape, show how we as a registry fit in, and then we'll dig into our role in protocol development and collaboration. And so this right here is an incredibly simplified spider diagram of the MMRV landscape. It could be 10 times as complex as this, but so what you see on let's see, your left-hand side is the NGOs. So these are the organizations like the nonprofits, the government that is focusing on, you can scroll down, on doing kind of research, the primary research, setting research goals, setting standards. And then on the other side, you have the commercial space where you have these MMRV companies and the CDR suppliers that are focusing on the tech of the monitoring and the measurement, but also the removal strategies. And in between these MMRV companies and suppliers, you have these validation and verification bodies, these VVBs, that do exactly what they say they do. They verify that the carbon removed has actually kind of been removed, but to do that, you need something to verify against. And so this is where Isometric comes in as a registry. We're writing these protocols which the VVBs can verify against, and we're facilitating this verification across the space. And in order to do that, we need to kind of be in tune with the latest science, the latest tech. And so that's why you can see here, we have all of these lines going between us and each organization here. So we're collaborating with research organizations. So collaborating on some DOE projects with Seaworthy and some other organizations to figure out MMRV, but also collaborating with the tech to see where that is in terms of verification. And so the protocols is what sets the bar to get those credits onto the registry. And so now we can spend some time about thinking about the protocols. And so I mentioned I would come back to this concept of rigor, transparency, and collaboration. That's what we're highlighting here. And so each of these aspects is the aspects that go into our protocols. And so on the left, thinking about a protocol as a rigorous framework for carbon verification, this is where the collaboration comes in, which we have a science network of over 200 scientists and subject matter experts who we engage on a voluntary basis and also a paid basis, depending on how much you want to engage. And so I'll talk a bit more about that on the final slide. But these two panels are the ones I want to spend a bit more time on. So thinking of a protocol as comprehensive guidance for suppliers on what data they will generate and what data that's recommended they generate in order to kind of address these issues of carbon dioxide removal. One thing I'd like to here kind of spotlight is this bottom panel of site-specific considerations. And so this is something we're thinking about a lot, because as CDR expands, you're going to be applying it throughout the world, from high latitudes to low latitudes, to different economic conditions, from lesser developed nations to greater developed nations. So thinking about how we can collaborate to make sure protocols are applicable and equitable. And finally, talking about this transparency aspect of building scientific growth through sharing data. One thing I want to call your attention here is the very bottom right, or the second one of recommended data collection. So we have two tiers of data collection. One is required for proving CDR. The other one is recommended. This is serves the purpose of kind of advancing the field. So the more data you collect, the less uncertainty you can have. And also you can facilitate this potential transition to more model-based MMRV. And so with the final couple of minutes here, I'd like to spotlight how we go about developing these protocols for MMRV. This is not dissimilar from how you would write an academic paper and go through the peer review process. We start with our internal science team by drafting a document with our consultants and collaborators. Then it enters this 30 to 45-day consultation period where we engage with stakeholders privately for a couple of weeks and then publicly out on the entire science platform to give comments. We've built this framework here where you can comment privately, and also you can have discussions in the comments on these protocols. And as of this morning, we've released a few protocols. We've received 525 comments already. And so we're looking forward to receiving thousands so we can iterate on these protocols from an operational feasibility standpoint for suppliers, but also from a research collaboration standpoint. And so spotlighting here which protocols and modules we have undergoing this method. On the left-hand side is the specific protocols. These correspond generally to CDR pathways, such as enhanced weathering, direct air capture, etc. And on the right-hand side, we have these modules. These are more applicable across all pathways. So something like transportation, energy use, that you can kind of plug and play and put these into a protocol. And everything here goes through this exact same consultation and collaboration process that I outlined previously. And so finally, I wanted to thank you for listening and engaging on this. One thing I want to note is this isometric science network. So this is how we really envision speeding up collaboration. So we have these 200 plus scientists. We'd really encourage you to join because you can do anything from comment on a protocol once a month, or you can engage in hourly consulting where you do a deep dive on a protocol, a method development, or a specific research idea that you have. So this is the QR code here, or reach out to me at the email address. And we'll be at a poster session later at 2:10. And so come find me and talk to me. I have two other colleagues here, Ella and Kevin as well. So thanks again, Gyami.
Thank you, John, for staying on time. And please hold your questions for the end, everyone. All right, the next talk is by Stefan Metzger.
Thanks, Gyami, for the introduction. I'm excited to be here. Thanks for joining. I'm going to talk about carbon due, anchoring equitable climate solutions in directly measured greenhouse gas exchange. So essentially, when we look at the carbon economy, there's primarily two branches. On the one hand, on the left-hand side, the branch that you see is unabatable or residual emissions. On the right-hand side, the branch that we see is additional carbon sequestration that can be used for offsetting. And they come together at the bottom in the form of carbon trade. So far that picture looks very nice and symmetric. Now that said, in the center, you see this kind of disconnect here, where essentially we use very different quantification approaches in either of those branches and even within the branches in individual carbon management sectors. And I think the question that we have to ask ourselves, the question arises, to which extent are these different approaches actually interoperable, meaning a quote-unquote ton of carbon quantified in one area of carbon management has, whether or not that has the same amount of molecules as a quote-unquote ton of carbon quantified in another area. And so that is something that the Carbon Community of Practice is setting out to help with. Our vision is that direct measurements of greenhouse gas exchange in and out of the atmosphere anchor fair and equitable climate solutions. And we're going to dive in a little bit deeper what that means and what the tools are that we can use for that. And our mission, to roll it out, is to bring together stakeholders across the entire climate spectrum to unlock cross-disciplinary expertise. So let's dive in. We're going to take a look in one or two of those modules and then put the whole puzzle together in a coherent picture. So direct greenhouse gas exchange measurements, what are they? How do they work? It is one approach, one very widespread approach is the eddy covariance measurement. And what it does is it's not just tracking concentration of greenhouse gases, including nitrous oxide and methane, but also CO2. What it does, it is also tracking the direction of those exchanges. So it's telling us whether this is directed to the surface, which would be sequestration, or whether it's actually emission, not just the pure concentration itself. It's done through anemometer measurements in sub-second resolution. So that's the wind measurement, that's the trajectory, where's our molecules headed. Then there's gas analyzers that track the actual greenhouse gas combinations, greenhouse gas concentrations, and then they're being combined to figure out where are our greenhouse gases going. Those can be mounted side by side on towers, but also vessels and aircraft and so forth. And in fact, there's thousands of these stations already operating globally that we can tap into. Now, the beauty of that is you can already tell it works at this quote unquote impartial interface between pretty much any surface below. So that can be, it can be a city, it can be industry, it can be agriculture, it can be forest, and the air above. And so that allows us essentially to derive such an impartial or interoperable benchmark across our carbon management sectors, but also across our different proposed and realized climate solutions. Now, the second part is how can we bring this methodology that's still fairly complex in its interpretation and that can be very expensive, how can we make that more market ready? And that's where that second module is coming in that we refer to here as flux mapping. And the way how that works is that this methodology, as we've been exploring it, it is an atmospheric methodology, which means it really matters literally where the wind is coming from. So it's essentially measuring a plume, and that makes it difficult to attribute it back to the ownership level, like was that emission from my plot of land or my neighbor's plot of land and so forth. So we really have to cross that bridge at some point to be able to connect it to carbon accountability. And so that's essentially what's happening with methodologies like flux mapping, where now we get this representation of an half-hourly map of hotspots and cold spots that are now on a common geogrid with any coexisting quantification methodologies that we can locate on a pixel-by-pixel basis and compare to each other on that pixel-by-pixel basis. And here's the end result. It's a study by Susie Wiesner, who is also sitting in the audience here. So on the left-hand side, what you see is this carbon dioxide exchange blob, quote unquote, that you get from a standard eddy covariance measurement. And that at the end of the day, when you're mapping these things out, then you get this beautiful definition that you see on the right-hand side. And I must emphasize that the contour lines that you're seeing here, they were actually superimposed after the fact. So after these exchange rates have been mapped out to kind of highlight how well this type of transcription process from temporal information to spatial information actually works and coincides with different management practices. Another example here, which aims to highlight how transferable that methodology is, that's from the oil and gas industry, actually, where you can see this was applied on an unmanned methane flux aircraft, seeking emissions from oil and gas industry, and inadvertently also finding emissions from wetlands here on the northeast corner, which again highlights how transferable and interoperable that type of methodology is across our different, both nature-based and tech-based carbon solution sectors, climate solution sectors. Now, what we see happening with this here is that we essentially squeeze a lot more information out of this type of existing flux tower or flux aircraft data than what was traditionally done over the last 7 decades. We see actually an increase in information content on the order of 10 to 100x, which in turn means that the price or the cost per unit area of something that is directly tracking the motion and direction of molecules in the atmosphere is coming down to achieve cost parity with approaches that are currently widespread in our different individual carbon management sectors, and allows us to make this type of intercomparisons and benchmarking a lot more accessible and also attractive from a cost perspective. and bringing this transparency, rolling out this transparency across our different management and quantification tools. So now let's put this all together back into the whole picture. So on the one hand, we have this impartial molecule tracking integrity that we can utilize based off the direct flux measurements. We can bring down the cost and the complexity by bringing it into formats and units that are readily accessible, that can be rolled out over Google Maps, that we can let loose our GIS scientists and integrate that and compare that and benchmark existing methodologies to a direct methodology, which then in turn provides a reliable stream and a 10 to 100x information content reliable stream for ground truthing coexisting remote sensing data, that in turn allowing a much more cohesive picture, 24/7, 365 global picture of what's going on in terms of our carbon, but in extension also water and other greenhouse gas cycling, making that accessible to the far right on the one hand for environmental intelligence, but on the other hand, also for public awareness. So imagine your weather app, and now you essentially have these carbon layers and other greenhouse gas layers in there. Okay, now here we can revisit essentially our carbon economy, and what's different now in this picture is that we're having this yellow bar, integrated MRV, or also R&D in terms of our climate solution development that was previously disconnected. And what that allows for is clarity, agency, and ultimately accountability, because the atmosphere is going to do a mass balance on this anyway, like we heard in the previous talk. And it's really up on us to be able to retrace those steps in a virtual way, so to say, in a scientific way, to be able to have any chance at all to move the needle with regard to carbon management. Last but not least, example activities of Carbon Due. Let's make science matter together. So we are working with several partners, as you see here, Black Swift, University of Wisconsin. We work towards open example maps for industry and regulations for try out these things and how much do they matter for specific applications. Tonight, there's also an upscaling fluxes workshop in case you're interested. So feel free to reach out with regard to that. We have a session this afternoon on surface atmosphere interactions, flux measurements for real world impact. There's a pod after that. And we also do activities like providing feedback and input, for example, to the request for information on the greenhouse gas measurement information system, where I think some of the people here on the podium have been very involved with as well, resulting in things like eddy flux measurements now being explicitly mentioned in some of those guidances. So if you're interested, it's free to join. You can find our address here, carbondue.org. And yeah, come and join us and we can figure this out together. Thank you so much.
Thank you, Stefan. All right, so our next talk is Maureen from Maureen McCarthy. Maureen, please join us.
Thank you. Thank you very much. And that was great talk just before. So I'll be sort of dovetailing into some of the comments that you made about the eddy covariance work. I'm Maureen McCarthy. I'm a research professor at Desert Research Institute. And I'll be talking on behalf of our team. Some of you may know Richard Giasone. He manages our EcoCell facility, and J.R. Nahn, who's the chief scientist in charge of most of the projects. So what I'll be talking about is quantifying carbon fluxes in a controlled environment, which dovetails to a lot of the work that you'll be discussing about quantifying measurement systems, but also being able to back up some of the field measurements that'll be discussed today. So what I'm discussing is work inside of the EcoCell facility at the Desert Research Institute. And the EcoCell facility has been there for about 20 years. I'll go into a little bit of a description about it. We have a list of our projects and publications available. For those of you who are unfamiliar with this, it's a ecologically controlled enclosed lysimeter laboratory. And I'll give you specs on what the original facility is. So we have the facility, it's been there since it was constructed originally in the 90s. It's capable of measuring right now. We measure total CO2 fluxes or continuously measure CO2 fluxes and evapotranspiration on intact ecosystems. So it's one of the few facilities in the world where we can look at intact ecosystems. It's particularly useful for arid and semi-arid and agricultural systems, but we can adapt to other environments as is required. And it's complementary to a lot of the field studies, including especially at Ecovariance Tower work that we do quite a bit of. What I'll be talking to you about today is a new project that we're doing that's upgrading that facility, just to let you know this capability is out there, and adding additional enhancements to the facility. This is a project funded by NIST. And so here's some specifications so you get an idea of what the scale of this facility is. It has 4 EcoCell lysimeters, so you can see there's 4 chambers there. Inside of each one are 3 containers or pots. This is a large facility. It's enclosed with inside an outside greenhouse, and we can operate the 4 EcoCells either independently or collectively if we use them for single experiments. So we have those containers that hold the soil can hold up to about 12,000 kilograms of soil. I'll show you an example of bringing some of that in. We can scale the temperature, so we have complete control over the environment in each one of the cells independently. So we can scale the temperature, the relative humidity, the airflow, and we can also look at concentrations above ambient for CO2. So we have the ability to do things in a controlled way that allows us to look at fluxes under current conditions and scale to future climate conditions. And that's incredibly important when you're trying to do verification. It really helps also as a validation source for things like standards and protocols. So this gives you just a quick rundown of what the current facilities are. As I said, we're looking at total ecosystem fluxes right now. So we're looking at CO2 and evaporation, evapotranspiration with inside of the ecocells, each ecocell. We also have below ground monitoring, so we can look at root productivity and soil water content and all of the aspects of the soils themselves. And then we also have a permit to import soils from anywhere in the world. So we can work with soils that come from whatever environment you want. The new capabilities in the facility that we're working on the installations of now are really helping us get more reliability and precision in the measurements that we can do there. So that's basic things like improving the control systems and improving the electrical reliability. But the biggest new capability that we're adding to the facility, thanks to the NIST funding, is the ability to continuously monitor soil fluxes in addition to ecosystem fluxes. So now we can pull apart the contributions from greenhouse gas cycling from the soils, and we'll also be able to expand in the soil work to looking at N2O and methane as well as CO2. So just to give you an idea of some of the projects that we've done in the facility to date, and I'm not going to go into these in great detail, but I will show you the example of the top one there. It was the cover of Nature in 2008, looking at climate variability on ecosystem fluxes when you had a particularly warm year on an agricultural system. So this was tall grass prairies in the facility. As you can see from this list of projects, we've done work for both the public and private sector. We are looking really to expand the facility work in that precision area where we can really quantify fluxes, whether you're using them for carbon crediting or you're using them to look at the impacts of climate change on future ecosystems. So, you know, the basics of the facility work, a lot of work that we've done, like we said, we've looked at a lot of soil systems, agricultural systems has been sort of the bread and butter, is really understanding the timescales and drivers and responses of the carbon cycle and sequestration. So obviously, looking at the impacts of net ecosystem productivity, and then looking at how changes in single factor or multi-factor controls affect that net ecosystem productivity. So you're looking at plant productivity, you're looking at the fluxes, you're monitoring continuously, and you do this for a long period. So some of these experiments ran for 2 or 3 years, controlling environmental factors in the facility. So temperature or CO2 concentration or both. So